But this talk is basically about, the various signatures of these compact objects, and using that, what can we do, and what can we do in future. So first, let's begin by talking about where they come from. Of course, remnants of stars will come from stars. And to talk about their formation, we need to talk a little bit about the stellar life cycle, this life cycle of a star. So this is roughly the life cycle of a star. On the left-hand side, what we have is the life cycle of relatively lower mass stars, smaller stars, like our own sun. Our sun is a very small star, according to astronomers. And on the right-hand side, we have the life cycle of massive stars. So what we have here is in this region, where these are the gaseous clouds, what we call nebula, where stars are formed. And as the stars are formed, by formed I mean the moment they start fusing hydrogen or higher elements at the hydrogen at their core. And the moment they start fusing hydrogen at their core, a new star is formed and they form a massive star. By massive star, what we mean is basically stars having masses 10, 20, 30 times the mass of our own sun. So, which is a huge, massive star. Now, these massive stars, what we call massive stars, are very short lived stars. And compared to the life cycle of our sun, they live for a small, relatively small period of time. Of course, still large compared to human lifetime, but uh, much orders of magnitude less than the life cycle of our sun. And as they finish, as they finish their primary activity as a normal star, they go into what we call a supergiant or a giant phase. What we mean by that? We mean that during this phase of star, the star stops fusing a significant amount of hydrogen at its core, and it expands many fold in radius. So that's why it becomes a supergiant, and its temperature becomes relatively much cooler. And by the end, when this phase is also done, what happens is the star uh, undergoes a very explosive event in which, like a nuclear thermonuclear explosion, it sheds all its outer layers in this big explosion, which we typically call supernova. And at the end of explosion, what is remaining behind is what we call stellar remnants. It can be either a neutron star or a black hole. So we will follow this life cycle. For low mass stars, this life cycle will be there, but that's not so much relevant for this part of the talk. This is another example, a real life example, where we can see this particular end state of a massive star. So this is our the famous Crab Nebula. And what you see here in these gaseous regions is basically after the supernova explosion has happened, all the outer layers of the star has been shed, and this is what you see in these regions. And somewhere in the center is left behind the stellar remnant of the stellar evolution, and this is where the crab pulsar is sitting there. And we can study this particular object very well. So, when we say the stellar remnants, the neutron star or the black holes, what are they? Just to introduce you to it. First, let's take black holes. We have all heard about them. They are one of the most exotic, most enigmatic objects that we can see in our celestial sky. So, black holes basically means the complete collapse of the star. Means in a star, gravity is balanced by some outward force that restores the equilibrium inside a star in a normal star. But in black holes, what happens is that there is no outward force to balance the force or inward force of gravity, inward pull of gravity, and it results in a complete collapse of the star, and that results in a black hole. So, who gives rise to this black hole? So, According to the life cycle of the stars that I just described, the massive stars which have masses even larger than 20 solar mass, 20 times the mass of our own sun, can give rise to a black hole after their life cycle has ended, following the path we just described. So black hole means because gravity has won over any other forces, it means that at the center of the black hole, this will be an object whose center the radius is zero and the density is infinite. In other words, it is what physicists like to call a singularity, where any physical parameters becomes infinite. Now that's a problem because whenever physicists like to call it a singularity, but they don't like to deal with them, that makes everything very less interpretable and less hard to deal with, more hard to deal with. So, is there any practical definition where we can work with and we can connect to the black holes that we can actually in reality see with our telescopes? So, the practical definition that we will start with would be black hole is an object whose gravity is so strong that nothing, if not even light, can escape its surface. So that's the a very simple definition that we'll start with. In other words, also we can say that at its surface, the escape velocity should be equated with the speed of light, and that will give you the some sort of a boundary of the black hole, what we like to call as the Schwarzschild radius of the black hole. The other type of stellar remnants I mentioned is the neutron star. This is also very cool, not as popular as black hole, but to me, sometimes even cooler objects. These are also formed in supernova explosions, but from parent stars, which have slightly less mass than the black hole forming parent stars. They stars who have masses between 8 to 20 times the mass of our sun will form a neutron star. So what happens in a neutron star? In a neutron star, as the gravity starts to collapse, there comes a point where the degeneracy pressure of the neutrons balances the gravity, thereby setting a new equilibrium. Meaning, all of us have read Pauli's exclusion principle, right? In Pauli's exclusion principle, what we see that no fermion, neutron is a fermion, can have the same quantum numbers, right? So in this case, what happens is that as the neutron starts to feel the lower energy state due to the high density, it quickly starts filling up the higher energy states as well because it cannot sit in the same energy state, thereby creating a degeneracy or excess energy and which is equivalent to excess pressure. And this excess pressure balances the inward force of gravity. And this a neutron star will typically have roughly, a mass of our own sun, 1.4 times the mass of our own sun, let's say. But imagine the entire sun being compressed to, let's say, the size of half the Hyderabad city, 10 kilometers. So that means if you do that, you will have roughly the conditions of a neutron star. And that means inside such a star, the density will reach extremely high values. And at the very core, what we have is that such a situation that the density reaches extreme values, which is even higher than the density inside a nucleus. The inside of the nucleus is the highest density that we know of. But inside a neutron star core, the density even can surpass the nuclear density. And that basically means that inside the core of the neutron star, the properties of matter becomes exotic. What do I mean by that? I mean that we can see superconductivity, superfluidity, and various other exotic phases of matter, even at very high temperatures. There was recently a very big news regarding superconductivity at room temperatures, right? Inside the core of neutron star, we see it all the time. But its nature of matter in such a situation is not very well understood. And neutron stars have few very cool properties. What are the other cool properties? First of all, they are very compact, 10-kilometer radius. We know, roughly their radius. They are very dense. So 1 teaspoon of neutron star material would weigh as much as, let's say, the combined weight of all the buildings in let's say, the city of Manhattan, which has many high rises. They are spinning very fast. They can spin as fast as 600 times in a second. So that means that we can see very cool activities happening that is a resultant of the high spin. And lastly, they are the objects in the universe who show the most strongest magnetic fields. The magnetic fields can be 10 to the power 12 times or 10 to the power 10 times higher than one of the strongest magnetic field we terrestrially see. So that makes them very exotic objects. So why do we need to study compact objects, either neutron stars or black holes? So I will give you three very broad reasons. One reason is just a little bit of a technical plot, but I will explain what this means. Here what we have is the curvature. Curvature basically gives you the strength of the gravity as a function of the gravitational potential. And you can see that the neutron stars and XRBs are the black holes, the normal black holes that I talked about, are in a region where you see the most dominant curvature for similar gravitational potential. What basically it means that even though gravity is typically a weak force, the effect of curvature, which gives you how strong the effect of gravity is close to a particular object, would be the highest close to the neutron star or the black holes. So in our normal day-to-day observations, whatever effects of gravity we see, they happen in what we call the weak field regime of gravity. And we know that Einstein has proposed the general theory of relativity to explain how gravity works, but there has been other explanations of how gravity works as well. So in order to figure out which theory of gravity is correct or how much, to what extent Einstein predictions is indeed accurate, we need to go into fields where gravity is in its strongest form, even though it's a weak force to begin with, weak range force to begin with. So, and that can only happen close to a neutron star or a black hole. So these are indeed exotic objects because you can do testings of all the theories of gravity close to these objects. On the left-hand side of this slide, what we have is, I will explain the mass and radius plot of neutron stars. So I just told you that the matter inside the core of a neutron star becomes exotic and it shows superconductivity, superfluidity at very high temperatures. Alongside it shows very exotic phases like pasta phase where the material is not just quarks or all the standard forms that we know of, but some exotic versions of them like free quarks, pasta phase, and so on. And we don't know how matter behaves in those situations. So what physicists have done is they have come up with interesting models as shown here, to predict how matter would behave under those exotic conditions. We know how an ideal gas behaves. What is the equation of state of an ideal gas? So these solid lines that you see are basically the equations of state of those exotic matter. The different proposed models that gives the equations of state of that exotic matter. And if we can measure clearly the parameters of a neutron star, the mass and the radius and similar quantities, we can pinpoint which one of these models is correct, or in other words, we can pinpoint what would be the equation of state of such an exotic matter condition. Okay. And lastly, this, as I said, neutron stars can show very extreme magnetic fields. So you can also study how physics happens at the most ultra strong magnetic field conditions. So these are the main highlights why compact objects are very cool objects to study. To give you a bit of a history, when they were first discovered. How do you get to know whether they exist or not? So one of the ways they were first discovered was by looking at them in something called X-ray binaries. So there are objects in the sky which are very X-ray bright, and one of the earlier X-ray telescopes, very early X-ray telescopes, saw that there are these bright X-ray objects, and we can see very steady pulsations from these objects, as you would expect from some neutron stars, and also alongside them, they show a radial evolution which will happen if this object is in a binary system with another companion object. So this was one of the very first detections of such compact object systems, particularly in binaries. And with that, the field of X-ray astronomy started, compact object X-ray astronomy. So I said that these are X-ray bright objects. So first question to ask is, why are these objects bright in X-rays? What powers this object emission? You can see here image taken by Chandra X-ray telescope, and all these bright objects that you see are basically this compact objects, either neutron stars or black holes in some binary systems, emitting in X-rays. This is a particular globular cluster, which is a cluster of stars containing a huge population of these neutron stars and black holes. So we can see they are bright in X-rays, but why are they bright in X-rays? So what happens is these objects are often seen in companion in an orbit with another star. Here is the companion star alongside the neutron star or a black hole is sitting somewhere there, here. And what this compact star does, by compact star I always mean a neutron star or a black hole for this purpose of this talk. It starts to accrete matter, pull matter from its companion star, and because the matter from the companion star has an angular momentum, it kind of forms a disk, basically slowly inspires, thereby falling onto the central compact object. And this disk is known as the accretion disk. This accretion disk is very hot. Even the gravitational field in this region is very high, and because this accretion disk is very hot, the frequency of the radiation emitted from this disk is very high, which happens to fall in the X-rays. And accretion, therefore, becomes the most efficient source of energy generation for this particular objects, and in general also, resulting in a huge copious amount of X-ray radiation being emitted from these objects, where a black hole or a neutron star is in binary with a companion star. You can do a small exercise to convince yourself. This is, of course, a hypothetical exercise where you take a hydrogen atom from infinity and bring it close to a black hole or a neutron star. And you can check the change in the gravitational potential energy and see that, how much energy would be released and what would be the frequency of radiation. Of course, this is a very toy model that I'm talking about. Anyway, these binary systems are where this matter from the companion star falls from the star to the neutron star or a black hole through the formation of an accretion disk to conserve angular momentum. And this disk, as I said, is very hot, having a temperature of about 10 to the power 7 K, and emitting significantly in X-rays. Surprisingly enough, though they are primarily bright in X-rays, they are not just emitting in X-rays. So this is roughly, let's say, the accretion disk, and sometimes we do see jets from these compact objects as well. And what you see is that though they are mostly primarily bright in X-rays, they do also emit in optical, in radio, in IR, and so on. And the wavelength of the radiation would often correspond to certain specific physical processes and certain specific components of the binary system, either from the jet or from the disk or from the base of the jet or from the companion star and so on. So in order to understand these objects, though they are X-ray bright, just looking at them in X-rays is not enough. And that's why we nowadays are moving towards broadband studies or multi-wavelength observations to completely understand the dynamics of the system and the origin of the emission from this various component of the binary. The second important, so the takeaway point from here is radiation in a wide band is needed to understand this object. The second important point is here what I show is the, let's say the flux from these objects versus time in different energies. And what you can see here, the flux is not stable, but it's changing. It's showing a very, very strong variability. So that means that it's not only sufficient to observe these objects at one time, but we need high time resolution observations of these objects to understand how they're dancing, if I can use the word. They're very fast evolving. To understand their fast evolution, we need very high time resolution observations. So high time resolution is also needed. And this variability can happen due to multitude of reasons. They can happen due to the various physical instabilities developing in the disk, accretion disk that I showed you, or there is a gaseous plasma sitting over the binary systems, which is known as the corona, and the plasma oscillations in the corona can also contribute to the variabilities that you see in the emission. And as you see from here, that the variabilities can strongly dependent on energy. Here you can look at the variability at the softer energy band, which is here, and the variability at the more higher energy band, and these two are not exactly following each other. Okay, so variability can also be strongly dependent on the energy as well. And not just that, we all have seen the very famous, no compact object talk is complete without the very fast image of the black hole, which was a seminal development. Though this is a supermassive black hole, but still it's a black hole at the end. And this image of the black hole that we all famously saw a few years back, of course, excited us. But at the same time, you should also remember that the black hole image is not one single image, but they did take image over different days. And if you keenly see these images on the different days, you will see that even in the image of the black hole, you can see the intensity pattern changing. The ring pattern, here it was bright, here is not so bright. In other words, the change in the intensity pattern, the variability is also seen in these images that was taken by the Event Horizon Telescope. So broadband high resolution simultaneous observations are the word of the day to understand compact objects. I have talked a lot about variabilities. So let's say that given the binary picture that I have constructed for you, using that, how can we talk a little bit about where the emission and how the emission is getting generated from the binary system? So let's look at a little bit about cross-section of this binary system. Here we have the central black hole, and here we have the cross-section of the accretion disk. And the orange region here is the plasma, the hot plasma region that I talked about, which is called the corona. So when you are looking radiation from the binary system, X-ray binary system, what you are getting is emission from the entire thing. So as to start with, what you have is thermal emission, we all have heard of black body, right? So black body emission coming from the disk, which is shown here in red. Then that emission can get into this corona that we talked about, and can undergo various non-thermal processes like inverse Comptonization and so on, thereby getting pumped up to higher energies. So you can get a non-thermal emission at higher energies, and that's roughly often how we try to model the emission coming from the compact object X-ray binaries. Though there can be more complexities to the system that is giving rise to the emission. And here we show a spectra of the resultant spectra of the emission that I have just described, which contains both the emission from the scattered corona as well as the thermal emission from the disk. What we can do if we can clearly study the spectra, the intensity versus energy of these sources, is a well-modeled spectra of these X-ray binaries can give us a good handle on how this disk is changing, how the corona is changing, and various parameters of the system like the inner edge of where the inner edge of the disk is, or what is the mass and the spin of the black hole, and so on. So one way to observe these objects is to studying the spectra of these sources, and thereby our own AstroSat telescope, which I will mention a little bit later as well, has been very instrumental. And this one of this spectra was taken using AstroSat only. Not just the spectra, as I said, these objects are also very variable, dancing. Dancing means that they can show all kind of changes in their intensities, and some of these changes in the intensities can be periodic, or what we call in some cases quasi-periodic. Quasi-periodic means they are not exactly repeating at the same interval, but there is some flexibility to the period where they are repeating, but they are still somewhat oscillatory behavior, showing somewhat oscillatory behavior. And these are famously called quasi-periodic oscillations. How we observe them? If we go into the power spectrum, meaning if you see I showed you the intensity versus time, and if you say that you take the Fourier transform or the power spectrum of that intensity variation, light curve, what you get is the power spectrum of the source. And in the power spectrum, you can see this peak, this very highly peaked structure. So this peaked structure corresponding to a particular frequency means that there is some oscillatory behavior that this particular source is showing at this particular frequency. And these are known as QPOs. And why quasi? Because as you can see, this is not one single frequency, but this is spanning a slight range of frequencies. And these are known as quasi-periodic oscillations. And they are not just observed at one single energies or one single frequencies. Often they are seen in twine. So often you see instead of one, there are twin QPOs present. And these QPO properties are also can be function of the energy band you are looking in. For example, this is at a low energy band, the QPO is not present. But surprisingly enough, as you are going higher and higher energies, you can see that this peak structure is gaining some strength. This is also what we saw in a couple of slides earlier. I showed you that the variability, the nature of dancing of the intensity of the black holes can also be different at different energy bands. We also see one exciting thing is that the neutron stars and the black holes both of them show QPOs, but the nature of the QPO they show are slightly different. Neutron stars tend to show a little bit more, higher frequency QPOs, where black holes typically tend to show towards, on an average, typically low frequency QPOs more. Where do they arise from, all these interesting QPOs that I've talked about? There are multiple scenarios, multiple models that physicists have come up with, astronomers have come up with, to explain why QPOs are happening. And they can be used to probe very close to the black hole and understand what kind of interesting things gravity is doing close to the black hole. To give you one example of the kind of scenarios that has been proposed is you can see here, this gridded region is the space-time around a black hole, and the central region, let's call it the black hole. Now, we roughly know that gravity can be manifested as a depression in the space-time, and also the black holes themselves, they have mass, which results in the depression and the gravity they manifest, but also they have something called spin. They are not a non-stationary black hole, but they have a rotation. So because they have rotation, that means that they are not just deforming the space and time, but they are also imparting a drag on the nearby space and time due to their rotation. And because of this effect, what happens is that there are certain perturbations created in the nearby space and time due to the drag imparted by the black hole on the space-time fabric. And this results in a kind of a precisional behavior in the space-time. And that results in the QPO oscillatory behavior that we see in the power spectrum. That's one simple model of understanding the QPO. Of course, not the unique one. Here you can see the example of how the QPO will manifest. If you look at this region, it shows a kind of a precisionary behavior very close to the nearby region around the black hole. And because they are happening close to the black hole and very intricately related to the spin and the mass and the gravitational effect of the black hole, study of this can help probe what is happening near in the vicinity of the black hole, and whether whatever Einstein's general theory of relativity has predicted are indeed consistent with what we are observing close to a very highly gravitating object or not. So the advantages of QPO, therefore, are they can be very helpful for constraining the parameters of the compact object like mass, spin of the compact object. They can be used to test Einstein's predictions. In the case of neutron stars, the QPOs can also be connected to the magnetic field of the neutron stars, and they can also be used to put possible limits of the magnetic field, as well as whatever activity like nuclear burning has been happening on the surface of the neutron star. However, even though they are such exciting objects to probe the vicinity of the compact objects, there are various challenges that we face in studying QPOs. One major challenge is, we see there is a wide variation in how QPOs are being exhibited by different sources, even, let's say, different black holes. And till now, there has not been a single model that can, explain all the behavior of QPOs from all black holes and how they're evolving with time or energy or frequency. And there are a lot of questions that are still existing with relation to them. And also, of course, I just said that the QPOs displayed by neutron stars and black holes are not exactly consistent. And the question arises why that is the case. We are nowadays looking at some QPOs of the black holes, and we see that they are not also stable, but they are very dependent on how the source is changing. This is an example of such QPO. This is the QPO that I have shown here, and what you see here is the QPO frequency, where the frequency at which this variability is repeating is a strong function of the accretion, the rate at which the mass is being dumped on the disk and the compact star. And they show a very one-to-one correlation, meaning the frequency at which this reputational behavior, the variability will be triggered, is basically dependent on the way mass is being accreted through the disk onto the black hole. Okay. And we also see not just the accretion rate, m dot here is the accretion rate, not just the accretion rate, but the QPO can also be very strongly related to how the source emission properties are evolving. For example, here the color represents the how much uh, the non-thermal emission is dominating the uh, emission from the compact object X-ray binary, the black hole emission. So we see that the more non-thermal the emission is, the higher the frequency of the QPO. Okay, so that also can be related. So in short, to kind of summarize, we see through joint spectrotemporal studies of QPOs that the QPO origin and evolution can be a strong function of how the source is emitting and how much the matter is getting dumped via the accretion disk to the source. Okay. The other interesting thing this object show, not the black holes, but only the neutron stars, is something what we call thermonuclear flares. So these are very intense flares. Huh. You can imagine the intensity happening like this, and suddenly there is a like a atomic explosion. There is a sudden sharp rise of intensity and followed by a slow decay. These are very short duration events, about let's say few seconds to tens of seconds. And these are known as bursts or flares. These are this happens due to thermonuclear explosion, and that's why it's fancily called thermonuclear X-ray bursts. What happens is that for neutron stars has a surface, and they accrete matter from their companion star in this binary systems. And as matter gets dumped and more on the surface of the neutron star, it kind of builds up a column. And if the accretion rate is significantly favorable enough, the temperature, pressure at the base of this accumulated column becomes so high that it reaches conditions to trigger thermonuclear fusion. And then it kind of acts like a atom bomb, where it triggers thermonuclear reaction in a very avalanche manner, thereby resulting in a very sharp increase of intensity followed by a slow decay as the fuel burns off and then cools. Okay, and this is an example of three thermonuclear bursts that we saw recently. And not only that, sometimes these thermonuclear bursts, as and when they cool, their intensity decays, they are followed by a kind of a smaller secondary bursts as well. Those kind of behavior are also seen, as you can see by the second blip that is shown here. And these objects are very, very interesting because they are happening on the surface of the neutron star. Often when we see activities from close to these objects in a binary system, we are not sure whether how much close to the compact object they are happening or where in the disk things are happening. But for bursts, because they have to have the accumulated column, we are completely sure they are happening on the surface. And that means that as much close to the gravitational field of the neutron star as possible. And they are, because they're happening from the surface, they are the best candidates for measuring the radius of the neutron star, which is one of the most difficult quantities of neutron star to measure. And remember when I showed you the equation of state of the exotic matter, we saw two parameters, the mass and the radius. The mass is relatively easy to measure, but if you can also measure the radius, you can put actual constraints on which equation of state of the exotic matter that we have been talking about is the most representative one. So these bursts are therefore the most promising candidates for measuring the radius of a neutron star. And apart from that, again, the challenge is that they show a wide variation in their properties, and depending upon how much fuel is getting dumped on the neutron star, what is the nature of the fuel, does it contain more hydrogen, more helium, or trace amounts of carbon, or so on. Where on the neutron star is getting dumped upon, all these factors affect the nature of the bursts that we see on the surface of the neutron star. The interesting properties of the bursts is when they happen, they basically show a thermal emission. It's a black body kind of an emission where the black body temperature roughly varies between about 1 to 3 keV. So here you can see the temperature of the black body in the very first panel as a function of time from the start of the burst. So here, ignore the colors for now, but basically what this shows is how the burst temperature, once the explosion has happened, then slowly the fuel cools off, how it changes with time. And if we can clearly map out how the temperature changes with time, and uh, this is the radius, how the radius is changing, then using this and using the simple Stefan-Boltzmann formula, we can put a constraint on the radius of the neutron star and thereby put a constraint on the equation of the state of the dense matter. But however, in some of our recent results, what we show that, slowly with highly sensitive observations, particularly, remember I talked about broadband, right? So if you have the luxury of doing broadband observations, what you see is that the burst spectra that I just mentioned is a simple thermal Planckian spectra, black body spectra, is not necessarily a black body spectra anymore, or not completely a black body spectra, but it actually deviates from the black body spectrum. Now, the question is, if it deviates, of course, that means that that will have, errors in the radius that we have estimated from using the Stefan-Boltzmann formula. So, and the question is, what is giving rise to this deviation? Uh, in some of our recent studies, we have tried to address this question: why and how we can answer the origin of the deviation from the standard spectra, standard Planckian spectra that we typically see for thermonuclear bursts. And what we see that if we have the luxury of again the broadband emission, we can study this excess and we can show that that can primarily arise as when the burst is happening, it kind of acts like a light that is shining it's not just coming to us, but it's shining the entire neighborhood, the disk, the corona that we talked about around the neutron star. And as it's shining the entire neighborhood, it's kind of interacting with the disk, with the corona, and whatever it is in the neighborhood of the neutron star. And thereby, it is significantly changing its nature. And sometimes it's changing in its effects is changing even the accretion flow that is typically dumping matter on the neutron star. So that means as a result of the burst and the accretion interaction, there can be a change in the nature of the burst as well as the change in the accretion flow. So a detailed understanding of this is needed before we can use burst to measure the radius of the neutron star. The other thing I'm very interested in studying close to the compact objects is the spectral lines. Till now, when I was talking about emission from the X-ray binaries, I was talking about what happens from thermal emission when we see thermal emission from the disk or the corona, the plasma region. But apart from that, we can see also very narrow, absorption lines or emission lines in the spectrum. How do they happen? Normally, the simple scenario is that there is this non-thermal emission from the corona that is being emitted, goes in all directions, and it also hits the disk. As it hits the disk, a part of it is getting absorbed, and therefore, a part of it is getting reflected. And as it's getting absorbed, we see some lines corresponding to the transitions levels of the elements that are present in the disk and taking part in the absorption. Here is a basic, theoretical model of how an absorption line would look like due to, let's say, presence of iron in the accretion disk. Now, in reality, how does it look like? In reality, you have to remember the line will not be as, ideal, and there will be all the signatures of the different physics that is present at the near the neutron star or the black hole on the profile of the line. So a simple classical line would look like this. Why this horn profile? Because remember, the disk is also rotating. It has an angular momentum. So some parts of the disk will be looking towards you, and some part will be going away from you. As it will be going away from you, the line emission from the disk that is going away from you will be Doppler shifted according to the velocity that is going away from you, or red shifted. And the part that is going towards you will be blue shifted. So therefore, it will give you a horn profile. But on top of that, there are effects of spatial relativity, general relativity, and different radiuses in that disk. So in the end, what we will end up getting is a line profile like this, which is a very skewed profile. But the interesting thing is that because all these effects are present, we can model this line to infer about all these effects, and in turn the parameters of the object that is sitting there. A short example of this is, let's say we have a black hole which is not rotating. So in that case, the accretion disk will only approach to a certain radius close to the black hole. But if a black hole is rotating, high enough, what happens is that we can show, following Einstein, that the accretion disk can reach very, very close to the black hole. And correspondingly, the profile of the line that we see is also different. Here you can see that the line profile is sharper and is falling very fast. Whereas for the spinning black hole, the line profile can be much more, can have a much longer tail. So just by looking at the line profile, we can measure, at least have an idea of how fast the black hole is spinning, and what is the mass of the black hole. And remember, for a black hole, these two parameters are one of the at least two of the three major parameters to completely understand the properties of a black hole. This is how the observational signature of a line can be very helpful. How much time do I have? Sorry.
Yes, I think 15 minutes.
Okay. Then I will take few time to go through it. And
Yeah, please.
sorry, yeah, a little bit to talk about a certain subclass of neutron stars. Till now, what I have been talking to you about is where the neutron star or the black hole is in a binary system. Because they are by themselves not that brightly emitting, so having them in a binary helps them to understand all this uh, uh, emission processes, because we get an enhanced emission from them. But there is another special class of neutron stars which is called the pulsars, which is another object very close to my heart. These pulsars are a subclass of neutron stars who have a very strong magnetic field, and they also have a very strong, typically they have a very high rotation. So what happens is that their rotation axis here and their magnetic axis here, they are not aligned. That means that as they rotate, the magnetic axis kind of sweeps out a cone. And because they have relatively higher magnetic fields, they emit radiation along their magnetic axis, and due to this misalignment, whenever the cone through which they emit sweeps our line of sight, we get a blip of radiation. So this is like a lighthouse. So whenever the lighthouse torch is pointing towards us, we get a blip. So the pulsars are also basically like that. They have typically the most highest magnetic field among neutron stars, about 10 to the power 12, 10 to the 13 Gauss. This is 10 to the 13 times the magnetic field we see on Earth. And their spin vary from about few milliseconds to the latest record is about few tens of seconds. And these objects are dominantly observed in radio, and they can be one of the best clocks because the period with which they rotate and send this blip of signals, here you can see a steady blip of signals that we are showing from a particular pulsar. They are very, very accurate. They are so accurate that they can be used as a clock to measure various exciting things in the universe. Again, to give you a brief history, they were first discovered by Jocelyn Ben Bernal using radio telescopes. Incidentally, this is also the first observation of a neutron star. This is how we got to know about neutron stars. And on the left hand side, you can see the actual data where she recorded the first detection of a pulsar. And this led to the Nobel Prize in Physics, though unfortunately she didn't get it. Anyway, to talk a little bit more about pulsars. So pulsars have been discovered like more than 50, 60 years back. Huh. But still, even after so many years, their emission mechanism remains enigmatic. Huh. We have still a lot of questions about why and how they emit and what results in the change in the variations. For example, even in the last slide, you can see all these pulses that are coming from the pulsar. They are not the same. Some are higher, some are lower, some are slightly different. Huh. And also, recently, what we have been interested in is something called the dancing of the pulsars, or in other words, what we call the drifting of the pulsars. What we mean by drifting? So here, if we look, each individual red line is a pulse, one individual pulse from the pulsar. So this pulse, as you can see, is not a one single sharp pulse, but it has substructures like this. Here you can also see the substructures. But if we stack the different pulses, the first pulse, then the second pulse, then the third pulse, then the fourth pulse, what you see is that the pulses kind of trace out a pattern. Here you can see that there is a kind of a line there that each of the subpulses are following. The phase is changing, but the change of the phase are following a line. And then it's repeating back, and then it's repeating back. So this is known as the drift of the subpulses in phase. So the pulses are not, though they can be, pulsars can be very nice clocks, the pulses themselves show a lot of variations. And in order to explain them, a lot of models has been proposed, and one of the primary one of them is that the pulsar beam, which is the torch that I just talked about, is actually not a monolithic beam, but it has a lot of structures in that beam. And here you can see this circles. These circles basically represent some sub-beams or some substructures which results from what we call sparks, like electric sparks close to the magnetic pole. So in the close to the magnetic pole, what happens is that there is a strong magnetic field, and corresponding to that, there is a strong electric potential that is created, and there certain electrical discharges happen. These electrical discharges result in this kind of sub beams in the pulsar, uh, in the main pulsar beam, and that results in the sub pulses. And not only that, the sub beams themselves then rotate within the pulsar main beam. So this rotates like a carousel, like in the fairground you have seen a carousel, which moves around. So with many seats. So this is also like a carousel. And this is known as the carousel model. And we have been looking at some exciting, such carousel behavior of pulsar beams in order to understand what is happening in this pulsar main beam and what is giving rise to these sparks, exactly giving rise to these sparks, and how these sparks are changing with frequency or along the height of the magnetic beam. And we saw that for various interesting pulsars, this pattern that is traced is also not a steady pattern, and it changes. So with our own GMRT, we were looking at some pulsars, and what we saw is that the same pulsar showed this kind of patterns for a certain period of time. Then after, let's say, few 20-30 seconds, it changed and it started showing pattern like this. Here you can see the pattern has changed very much from this one, where this is not as consistently bright, or these are more broken patches, and also the slope with which the pulses drift in phase has also changed. The correspondingly pulse profile has also changed, and also a few tens of seconds later, to change to another mode. So this is what we call the subpulse drifting modes, and we see that the way they change the mode is dependent on how many sparks are generated in this carousel pattern that I talked about. This carousel pattern that I talked about, and depending upon where in the above the magnetic pole the sparks are getting generated, this pattern can be dependent on that height, that emission height. Not just that, we saw that this carousel behavior, this drifting behavior, can also be very different from pulsar to pulsar. We see that for recently discovered pulsar, uh, here you can see the pulse emission as a function of time over different observations. And there are few things to note here. One is the gray regions are the regions where the pulsar was emitting. But there were a significant number of regions or significant seconds where shown in white here, where the pulsar was not emitting at all. These are what we call nulls or pulsar nulling. And for this pulsar, you can see that it's a very inconsistent pulsar. Suddenly it's emitting, then it's off, then it's on again. And in the second observation, it's being on and off more frequently. Not only that, in the times where it was on, we see that it shows a drifting behavior, like the previous slide. But in this case, within a particular drifting mode, the drifting behavior is not steady, but it's evolving. It's systematically evolving. So that's kind of a new behavior. That means that the carousel model that we had talked about is not just enough, because what we can see is that here we show the different drifting pattern of this particular pulsar, and you can see that here the drifting rate, the way the pulse phase changes with the pulse number, slowly slows down, whereas in the other case it's slowly increases to faster and faster rate. In this particular case, it remains steady, it does not change. It has a drift rate, but it doesn't change. In this particular case also, it has a drift rate, it doesn't change. So it shows all kind of different drifting behaviors. Sometimes it's drifting with a fixed rate, sometimes it's drifting with another fixed rate, sometimes it's drifting with moving faster, slower to faster, and sometimes it's moving faster to slower. So how can we explain that? Sorry, just a second. So there's some problem with the GIF. But basically, the model that we can be used to explain this behavior is that the simple carousel with the sub beams that I explained to you will not enough. And here, that sub beams that you can see here, this small cones, they are the sub beams, and they are not rotating at a steady rate, but they are kind of suddenly spinning up, suddenly spinning down. This is not the pulsar rotation rate, but this is a rotation rate of the sub beams within the main pulsar beam. And this is, as you can see, suddenly spinning up fast, and then suddenly slowing down, and then suddenly steadily increasing. And that can be related to how the electric and the magnetic field are changing very close to the pulsar magnetosphere, thereby changing the sparks that is generating the subpulse subbeams. Okay. So a lot of interesting things to do with pulsars, but why are we really interested in pulsars? First of all, of course, understanding their emission at high magnetic fields is a very cool thing. But they are also very accurate timing clocks. And because they are very clocks, understanding their emission will help us use them as clocks, thereby we can use their properties to time various events that are happening in the universe. And what do I mean by that? I mean that if, let's say, a signal is coming from somewhere to us, where this is Earth, where we are sitting, and if there are pulsars in between, so the signal that is coming, the signal that is coming is intervening the emission from the pulsar. It will change the arrival of the next pulse. So there will be a delay in arrival of the next pulse because the signal has passed through the intervening medium between us and the pulsar. So by measuring this delay, then we can predict what has passed between passed between us and the pulsar. And using this, we can use to time various events in the universe. For example, we can use it for to time use timing for navigation in deep space for interplanetary missions as well. But more importantly, we can use them to measure gravitational waves. And this is basically a main tool for searching for continuous gravitational waves that is coming from all across the universe to us. And this particular thing is known as pulsar timing, where India is also involved along with various other facilities all around the world. And of course, I should mention that there was a very recent discovery, like a couple months back, where we actually the pulsar timing team detected a background of continuous gravitational wave, which is coming from all across the universe, possibly coming from mergers of supermassive black holes. And that was detected by timing all these pulsars that are all around us. I think IIT Hyderabad is also involved in this effort, and of course, more reason for you guys to be excited. And this is a remarkable discovery, and we hope to, see more exciting results coming out of pulsar timing, particularly in regard to detection of gravitational waves. Okay, having said that, I will just skip to the last part of my talk, which is talking a little bit about what we use to measure and observe these objects. So right now there is a bunch of facilities, both in X-rays and radio. I am mentioning these two wavelength band because for today's talk I have mainly covered these two observations, but they are by no means comprehensive. So we can use a bunch of X-ray observatories like XMM Newton, Astrosat, Suzaku, Chandra, Swift, NICER, and no one is better over the other depending upon the science case. Each of them has their own unique properties that can help us in this chasing and finding the signatures that I have talked about for today's talk. In radio, we have UGMRT, MWA, VLA, which can help us in studying these compact objects. Particularly Astrosat and GMRT are the Indian missions and doing great science. And hopefully some of you may be getting your hands dirty with them. But again, a large part of the talk had data and maybe some results also used from Astrosat, which is India's first multi-wavelength space observatory. It's a very unique mission which has 5 payloads, and as a result of that, using all these 5 payloads together, you could cover a large wideband wavelength range, as well as fast timing capabilities were there, which resulted in very, very exciting results. This is a comparison of the sensitivities, effective area, as a function of energy for the various missions that are there nowadays. And this is LAX-PC, which is one of the instrument on board Astrosat. You can see that it's sensitivity-wise, it's doing great, particularly in the higher energies. And this has resulted in, not just Astrosat, but all these observatories together has resulted in very, very almost path-breaking results in very recent times. For example, obviously, LIGO resulted in gravitational wave detection from merging of neutron stars, which not only had the gravitational wave emission, but also the electromagnetic counterpart, and gave us some very crucial clues about how merging happens or what happens when two such dense objects merge. We had the image of the first supermassive black hole. We mapped the new, close magnetic field behavior of the neutron star magnetosphere using NICER. Huh. Evidence of lens thinning precision. This is the frame dragging effect due to the rotation of a compact object on the nearby space and time. Huh. The discovery of very extreme energetic X-ray sources, but coming just from pulsars, were also done in very recent times. And evidence of this continuous gravitational wave, which was just last month. So a lot of exciting discoveries have happened due to with compact objects in the very last few years. And in future, there are a lot of exciting observatories that are going to come up, which can aid all these efforts manyfold. For example, in the radio, we'll have the SKA, which India is also probably will be a part of. Then you will have the 30-meter telescope in optical, Athena in X-rays, and few other telescopes as well, not just Athena. And finally, the Indian LIGO will come up sometimes in the next few years, which is going to change the the direction of this field, hopefully. There are other future missions. Particularly, I would like to mention, which I didn't spend a lot of time, but polarimetry, which is a new window to study this kind of objects. And this year only, India is going to launch XPOSAT, and POLIX is one of the polarimeter instruments on XPOSAT, which is not just going to do spectroscopy timing, which I talked about, but also going to do polarization studies, which is a relatively new window. And therefore, combining all this current and future missions, in future we expect many exciting discoveries to come. With that, I probably end my talk. Thank you for your patience.
Thank you, Dr. Manoneeta, for such a nice and such a information-rich presentation. It's actually really nice. Uh, may I ask you, like, is it okay if we record? We actually have recorded your lecture. We also have our own YouTube channel. Is it okay if we upload and share the video with, because some of the faculties and students have requested me, because they don't, I mean, they were not able to attend your lecture, to share a recorded copy.
Sure. Sure.
Okay, okay. Thank you very much. Actually, your lecture also helps me. Some of the students also wants to do projects in different parts, fields of the astronomy, and I believe that your recorded lecture will actually help me to give them a background on compact objects. It's so nicely
That
covered.
would be a pleasure.
Yeah. Now I'll ask the participants who are present here, if they have any questions, they can actually unmute and they can ask the questions. Yeah, Shri, please go ahead. Hello.
Okay.
Yeah.
So thank you, ma'am. First of all, it's very insightful talk. Like you covered all the wide range of compact objects, neutron star, black hole, and X-ray pulsars. So my question is regarding to the QPO.
Sure.
Like, are you doing any fitting to know at high energy is like null thermal component is dominant, or how we can know without fitting that at higher energy their non-thermal component is dominating actually?
Uh, you are asking at higher energy whether the QPO is getting enhanced, or are you talking about the spectral emission?
In the case of QPO, how we get to know that higher energy it's dominate?
Oh, that you can do by actually doing, yeah, you have to do some numerical analysis by doing some fitting and calculating the strength of the QPO in terms of what we typically calculate is basically the RMS fractional variability. So compared to the normal variability, how much is the fractional variability of the QPO, and you can plot it as a function of the energy to figure out whether the QPO is getting, the strength of the QPO is getting enhanced with energy or not.
So, ma'am, which kind of model we can apply actually for that?
Just for the power spectral fitting, we do typically use a Lorentzian.
Okay, so me also working on that strong gravity region of black holes. So I'm just little bit want to explore about the QPO.
Sure,
Thank you.
sure.
Thank you, ma'am.
Yeah, pleasure. Any more questions?
Anyone else have questions? Please
Hello.
ask. But yeah, go ahead.
Hello. Good evening, ma'am.
Good evening.
No, so my question is that is there any periodicity in the thermonuclear X-ray burst, um,
Oh,
or
okay.
quasi periodicity?
That's a very, very exciting question. So, there can be two periodicities related to bursts that we can talk about. One is, let's say a burst is happening, and during the burst, if there is some, change, a periodic change in the intensity. So that is also there. That is known as burst oscillation. So the idea is very simple. Let's say, I told you that the thermonuclear burst happened due to a thermonuclear fusion reaction on the surface of the neutron star, right? So imagine at one point of the neutron star, imagine a neutron star to be a ball, and at one point of the neutron star, there is a thermonuclear explosion or thermonuclear, burning that has started. And then again, this neutron star is rotating, right? So whenever the point where the burning is happening is facing towards you, you get a rise in intensity, and then it goes down. So that results in an oscillatory behavior. So this is known as burst oscillations.
Okay. So is there after some time again matter is accumulated and again a thermonuclear burst happen? So is
Okay,
there
so
any?
that's the other type of recurrence or the other type of periodicity that you were talking about.
Hmm.
Yes, that also people are trying to study. Uh, yes, there has been some cases where repeating bursts have been seen, and what we have seen is that the it's repeating at a particular rate, and the recurrence rate is of course a function of how matter is getting accumulated. Huh. But the problem is that the time period of the next event to happen takes a little bit of a longer time. Huh. It's a
Yes, ma'am.
significantly long time, and we don't have observations usually that long because of
Oh.
many different constraints related to satellite orbits. Huh.
Mhm.
So that means you will have a gap in your observation, and the moment you will have a gap,
Mhm.
then you don't know whether a burst has happened there or not.
Yes,
Right.
yes, yes, ma'am.
So your measurement of a burst or a recurrence period may be a little bit has some uncertainty.
And I have one more question, ma'am.
Sure, sure.
So the effect of drifting in pulses and pulsar nulling. So it is due to the any change in the magnetic field of the pulsar, because
Um,
all
yeah,
these effects can be or could be due to the change in the magnetic field or any structural change on the surface activity, something like that, due to the intense gravity. Like chirping, I know that quakes, like things on the neutron star
right.
surface.
Not okay. That's a very good point that you have again raised. But these particular events are not that related to quakes, or at least that's not that thought to be that related to quakes, because there are other events which are typically related to quake kind of events, and they are typically more explosive, meaning they result in more, explosive kind of event, more energetic events, and they should not be that stable. Quake kind of things are coming from stress developed inside the star's inner crust,
Okay.
and that are typically a little bit less coherent, less stable processes. Huh. Whereas these particular drifting patterns, I showed you a lot of variations, but still they are quite stable, at least within a short time scale. Huh. So that's why they are related to this sparks that we talked about, which is coming from the strong electric. It's related to the magnetic field. To answer your questions, the first question, the change in the magnetic field, at least the overall magnetic field, is not that high in a short time scale. The neutron star or the pulsar magnetic field do indeed changes, but the rate of change is very slow. So it's not enough to the change itself is changing the global magnetic field is not enough to trigger such an event.
Okay. Thank you, ma'am.
But it's more related to the the local plasma processes that are happening in the close to the magnetosphere.
Okay. Okay. And one last question, ma'am.
Sure.
So you said that there is a shift in the Planck black body spectra.
Yes.
So it is due to that we our models don't consider the GR effects, or we calculate the R ISO for neutron star, something like that, to uh, means uh, uh, calculate that R ISO, that GR effect is there. So due to that, these effects are there in the Planck spectra, in the black body spectra.
Right. The GR effect will indeed change the Planckian spectra a bit, huh? But that's not the only thing. Hmm. If that was the only thing, the effect will not be such a okay. One simple answer is, if GR effect was the only thing, that would not have been a varying effect, right? Because the GR effect that you were talking about, probably that you were talking about the gravitational redshift, huh, that is primarily a function of the mass by radius ratio. Huh. And the mass by radius ratio is not changing that much for a particular neutron star at a given time.
Okay.
Right.
Okay. Thank
And
you, ma'am.
what we see is the deviation is a very fast evolving function of the burst intensity.
Yes. Thank you, ma'am, again.
Welcome, pleasure.
Yes. Any other questions? Okay. If not, actually, uh, while taking the course, the students ask two interesting questions, which I may ask.
Sure.
One is like, uh, if you do not see the pulses, then how do you know the neutron star is rotating?
Mhm.
And second is like, when these two neutron star, let's say having two solar mass, and they are merging, and let's say there are two black holes, let's say four solar mass, they are merging. I mean, do we see any significant difference in the gravitational wave? I mean, are you expecting to know whether they are coming from a neutron star or a black hole when their masses are close? These are the two questions I used to get, but
Okay.
probably you are an expert, so.
Not, yeah, I can try. What was the first one? Sorry. What was the first one?
First one is, let's say you don't see the pulses.
Ah, okay, okay. Yeah, yeah, I remember. Huh. Yeah, that is a little bit difficult. If you don't see the pulses measuring the spin of the neutron star, it becomes a challenge. There are some ways. One is if you have a burst oscillation,
Okay.
right? So that's one answer. The other is it becomes like a black hole problem. So however, whichever way you measure the spin of the black hole can be
Okay.
applied for the case of neutron star, like through spectroscopy or the,
Okay.
let's say, some QPO studies.
Okay.
They can also put constraint on the spin of the neutron star.
Okay. Okay.
The other question is a more trickier. Yeah, if the masses are close, it becomes a challenge.
Mhm.
Ideally, the sharp uh, length, or in other words, the sharp is an exponential function, right? So
Right.
the exponential decay constant will be a function of the mass.
Okay.
Huh. So if it's not 2, it's 4, then definitely it will be different. But yeah, how much uncertainty will that have to distinguish the scenarios? Of course, that probably the
Yeah.
gravitational wave
Maybe
people can say. It's
some kind of simulations.
yes, yes. 10 2 can be very well distinguishable. I show whenever I talk about
All
gravitational
right.
wave. You can clearly see the chart is different. It's
Mm-hmm.
longer. Its intensity is shorter. uh,
Hmm.
because it depends on the mass function, which
Right.
is a function of the mass ratios, basically.
Okay. Okay. Great. Thank you, Dr. Monita.
Pleasure.
Yeah. Anyone else have any questions? If not, let's thanks, and we hope to see you in person
Sure.
in near future. Yes, please go ahead.
Yeah, no, sure, sure. It was a pleasure giving a talk here, and definitely, yeah, I look forward to someone being there sometime.
Okay. Thank you again, and we'll be closing the session now.
Bye, everyone.